Okay, so let's begin. Um, so basically, in chapter two, we're first. It's mostly about continuity and um, completeness of space and how that affects the maps. So for that, we'll need some topology, like Baire category theorem will be our main tool, which we'll use here to prove various things. Um, so first of all, for that we'll need some definitions. So first is nowhere dense set. So dense set, we know whose closure is the whole set. Like if X is a space, then its subset is dense if the closure is the whole space X. So nowhere dense is basically kind of the opposite way. So if S is a topological space, then E is nowhere dense if the closure is empty. So instead of the whole space, we got going nowhere. So nowhere dense. Yeah. So
You mean the interior of the closure, right?
was it interior of the closure? Let me check. 1 second. Okay.
And if the closure itself was empty, then the set would be empty.
Oh yeah, because yeah, sorry, yeah, my bad, yeah. So yeah, the interior of the closure is empty. My bad, yeah. So it's kind of the opposite. So um, so from this we'll define two types of set. So first, let S be a topological space like usual, and then we take a subset of S and call it of first category if it's a countable union of nowhere dense sets, and if it's not countable union of nowhere dense sets, so then it's second category. Category kind of sounds like category theory at this point, but just take it as normal classification of sets. So and some textbooks refer them as meager and non-meager set. That's kind of better than category in my opinion, but whatever, like we'll go with the category for now. So here are some categories of, I mean, properties of categories of sets. So first of all, if A is a subset of B and B is of first category, so is A. So here, like, this is kind of obvious to see, like uh, if B is a intersection of, I mean, sorry, union, right? I forgot. Yeah. So if B is the union of countable many nowhere dense sets, so if A is a subset, we can take A intersection those sets. So their union will become A, and since their interior of the closure were already zero, so A also, I mean, those I mean, after taking intersection with A, they still remain nowhere dense. So A becomes in the first category. And then any countable union of sets of the first categories of first category. This follows from the fact that since you're already taking countable union of nowhere dense sets, so countable union of countable union is also countable union because n cross n is in bijection with n. Like you can find a bijection like using the diagonal argument and stuff. So that from there we get this, and the second last two are not that obvious, but I really didn't get to the proof of them properly. So any closed set E, subset of S whose interior is empty, is of the first category. So I guess, like, if the interior is empty and it's closed, so then the closure is itself. So interior of the closure is empty, so then it is in itself nowhere dense. So we don't even need countable union, it's just already a nowhere dense set, so it is in the first category. If H is a homeomorphism and if E is a subset of S, then E and H of E has the same category in S. So basically here, since H is a homeomorphism, so it will map nowhere dense sets to nowhere dense sets, and the inverses will also work the same. So due to the homeomorphism, I think the countable unions will also work. Like countable unions of nowhere dense sets will also get mapped to countable union of nowhere dense sets. So they will have the same category. So if it's in the first category, E is in the first category, then HE will be in the first category, and vice versa. So that's that. And now we come to the main theorem, which is the Baire category theorem. So if S is either a complete metric space or a locally compact Hausdorff space, then the intersection of every countable open dense subsets of S is dense in S. So now this allows us to look at the categories and how they react in this case. So in this case, so if we look at a first category set, which is countable union, so countable union of nowhere dense sets. So then what happens is, if we take the complement, so then that becomes basically dense set, I think. Like if you take a nowhere set, nowhere dense set, and then take its complement, that becomes an open dense subset. So then that falls on the countable union. If you take the if you take complement of countable union of nowhere dense set, then that will fall under this criteria, that intersection of every countable open dense subset. But since that is dense, then we take the complement again, then we'll get that it'll still belong in the same type, like it still stay in the first category. So
just a small comment.
Yeah.
That's all correct, except it's the closure of a nowhere dense set has an open dense complement. But aside from that, everything is correct.
Yeah. Thank you for that. So now we'll go to the proof real quick. So we'll take the countable dense open subsets of S. Okay, so this is a countable collection of dense open subset. So we take an arbitrary non-empty open set. So if now then if we take an open Bn minus 1, so then since Vn is dense, so there exists open B which is not empty. So there exists an open set B which is not empty, such Bn, I think. Sorry with the mistake, open set Bn not empty, such that Bn closure will fall under Vn intersection Bn minus 1. This happens because Vn is dense. So in the first case when S is a complete metric space, so there we can take Bn to be of radius less than 1 by n. So like we can shrink it lower and lower. And in the second case where it's locally compact, so since it's locally compact, so Bn minus inside Bn minus 1 we can find Bn which is compact, so we can choose Bn to be compact itself. So then after doing that, choosing Bn's like this, we can take their intersections of the closures. We take intersection of the closure. So now when S is complete matrix space, then Bn's form a Cauchy sequence because the radius is shrinking, so it's getting closer and closer. So then which will converge somewhere in K, to some point. So K will be not 0. So and in the case when S is locally compact Hausdorff, so since K is compact, then K is also non-empty since locally compact Hausdorff. And from this construction, so we were starting with B naught and then keep putting a ball inside that basically. So K will sit inside B naught, and k is a subset of Vn for each n, since by construction Bn is in Vn as well, and Bn closure is in Vn, so k is in Vn. So for each n, so B naught will intersect intersection Vn, because k is inside B naught and k is inside Vn for every n. So that's how this concludes. So intersection, I mean, we have taken an arbitrary open set, and ultimately we showed that it intersects the countable intersection of dense open subset. So that's how we conclude the proof. And so now we'll see some application of Baire category theorem and the categories in the our linear algebra esque setup, basically with the topological spaces, vector spaces. So first we'll look at equicontinuity and uniform boundedness. What that means, I'll show you. So first, let x and y be topological vector space, and we take a collection of linear mapping from x to y, let's say gamma. So we say that gamma is equicontinuous if for every neighborhood w of 0 in y, there corresponds a neighborhood v of 0 in x, such that lambda v is in w for all um, lambda in gamma. So basically what it says is, so for every um, linear map from x to y, if there is a single neighborhood such that its image is always inside a open neighborhood. I mean, if we take an open neighborhood in the image, there will be an open neighborhood in the domain such that it gets mapped to that open neighborhood for every single linear map. Then it said that that gamma is equicontinuous. So basically all of them are all of the maps in that collection is continuous at the same time, basically on the same set, like they kind of behave together at the same time, if you get me. So this forms a relation between equicontinuous maps and uniform boundedness. So that's basically the fact that the for all of them, like for every lambda, the image is basically bounded. That's what uniform boundedness is. Like they all of the maps in the collection will follow similar bounds, basically. So hence the uniformness, kind of like uniform continuity if you look from real analysis perspective. There it was like all of the sets in, I mean, it was from entire domain, and here it's for all of the maps. So now we'll look at the theorem preceding uniform boundedness principle, or Banach Steinhaus principle. Sorry for the pronunciation if it's a problem. So suppose x and y are topological vector spaces. Gamma is an equicontinuous collection of linear mappings from x into y, and E is a bounded subset of x. Then y has a bounded subset f, such that lambda E is in f for every lambda in the collection. So basically, it's basically giving us a bound, basically. So if we take a image, if we take a bounded subset and look at the image of it, then that is also going to be basically bounded for every map in the collection. That's what the theorem says. So for proof, we just look at the union of sets lambda E. If we show that this is bounded, that should be enough. So W is, we take W to be a neighborhood of 0 in Y. So since gamma is equicontinuous, so there will be a neighborhood V of 0, I mean containing 0 in X, such that image of the image of V is in W for every map in the collection. This is by definition of the equicontinuity. So now as E is bounded, there will be a T for sufficient large T such that E will be inside T of V. I mean T times V. So we scale V large enough so that E falls inside it. We can do that since E is bounded. So for that T, lambda of E will be a subset of lambda of TV, which is basically T of lambda VB, since lambda is linear and lambda V is in W, so T lambda V is in TW. So from there F will be, I mean, so yeah, so from there we'll get that what do we get again? Yeah, so from there, like, this becomes a bounded subset, I mean bounded open neighborhood of 0. So basically then if we take F to be equal to TW, then F is bounded and so is, I mean, then it covers lambda E. So we'll use this to prove the uniform boundedness principle, which is also known as, I mean, mainly known as Banach Steinhaus Theorem, which says the following. So suppose X and Y are topological vector spaces. Gamma is a collection of continuous linear mappings from X into Y, and B is the set of all X in X, whose orbits, which is the images of, I mean, collection of images under the linear maps, basically lambda X, lambda is in gamma, so whose orbits are bounded in Y. If B is of second category in X, which is not the first category, which is countable union of nowhere dense sets, then B is equal to X and gamma is equicontinuous. So basically what it says is, if we see that it's pointwise bounded, so if it is pointwise bounded, then on a set which is of second category, then the set itself is the whole space, the subspace, I mean subset is itself the whole space, and gamma becomes equicontinuous, which if we use the previous theorem on that and then use a bounded subset, then we'll see that it is also uniformly bounded, like for the whole space itself, the image will be uniformly bounded for every single gamma, I mean lambda in the collection. So the proof is a bit longer. We'll pick balanced neighborhoods W and U, so that W is minus W, U is minus U, around 0 in Y, such that closure of U plus closure of U is in W. So we can do that, and then we'll take construct E as the inverse of U closure, and then take intersection of all such, I mean for all lambda. So then if X is in B, which is basically when it becomes bounded, the orbit becomes bounded, then gamma of X is in NU for some n, since X is, I mean orbit is bounded, so it must be inside some scaled form of U, since U is near 0. So then it implies that if gamma x is in is in nu, so then x will be in lambda inverse u closure for every nu closure for every nabla in lambda in gamma. So from there, just bit of an set equality to conclude that x is in ne. So consequently, from here we get so from here we get that b is in inside of union 1 to infinity ne, because for every x we can find an n such that x sits inside ne, so x sits inside union of ne from 1 to infinity, so b sits inside that set inclusion property. So then since b is of second category from the theorem, like from our assumption, so since b is of second category, then at least one of ne is of second category, because if all of them are of first category, then the union is also of first category from the first property. That would imply, from the second property. And then since b is a subset of this union, countable union, then that would imply b is of first category, which is a contradiction to our assumption. So one of the ne will be of second category. So now as x goes to nx, the multiplication by n is a homeomorphism of x onto x, since topological vector spaces. So E itself of second category, since that's the force property which we discussed. So but E is closed because each of them are continuous by definition, like collection of continuous linear maps. So each of these are closed. So since we are taking arbitrary intersection, E becomes closed. Since E is so okay, so yeah, E is closed. Then E has an inferior point of E, let's say x, since like E is closed and of second category and non-empty. So E has an interior point x. This follows from property 3, I think, of the Baire category. I mean, the properties of the first category. So it has an interior point since it's closed and of second category. So then consider x minus e. It will have an neighborhood of 0 in x with the following property, such that neighborhood v and lambda of v, which will be subset of lambda x minus lambda e, since x minus e will contain a neighborhood of v. So lambda v will be inside lambda x minus e, and then by linearity it breaks to lambda x minus lambda e, which sits inside u closure minus u closure, which basically sits inside w for every lambda in the collection gamma. So then this basically proves that, like, since this is true for every lambda, then by the definition of equicontinuity, gamma is equicontinuous. So since it's equicontinuous, then from the previous theorem, like this one, so gamma is uniformly bounded. So in particular, each gamma x is bounded by y. So then from here we can conclude that all of x is basically makes the orbit bounded. And basically, for any point we take in x, this becomes, I mean, lambda x becomes bounded. So yeah, that I think concludes the proof for um, uniform bounded principle. Technically, there are different versions of uniform bounded principle. This is probably the most general one. Like, there are special cases that we use. So yeah, so now we'll see some of them and some applications of uniform bounded. Um, so yeah, so now we know from Baire category theorem that F spaces are second category because like they are complete metric spaces. So from this and the previous theorem we get this corollary. So if gamma is a collection of continuous linear mappings from an F space X into a topological vector space Y, and if the sets gamma x, which is the orbit basically, are bounded in Y for every x, then gamma is equicontiguous. So basically here what happens is we are taking this to be an F space because like so that every single set becomes a second category set. So here like in the uniform boundedness principle, see we assume that B is of the second category. We don't need to assume that because it's going to be of second category by default from Baire category theorem. So just taking X to be an F space, we can just directly conclude that gamma is equicontinuous from the fact that the orbits are bounded for every X. So now if we take gamma to be a linear functional, like taking Y to be R, so yeah, so this translates to linear functionals if we take Y to be R, and gamma being equicontinuous will be similar to being uniformly bounded. So that generally is what we use for linear functionals and for like norm of linear functionals when Y is a normed space. So yeah, and also we can use uniform boundedness principle to find out limits of sequence of continuous linear maps. So the theorem goes like this. So suppose x and y are topological vector spaces and lambda n is a sequence of continuous linear maps. So again a collection of continuous space, I mean linear maps. So if we take C to be the set where lambda n, the image of lambda n becomes Cauchy, because for each x lambda n x becomes a sequence on the image y. So if it becomes Cauchy, then and if C is of second category, then C is equal to x. And if L is L is the set of all points where lambda x is just limit of lambda n x, basically when the limit exists. So if this set is of second category and if y is an F space, then L equals x and oh, I think this should be lambda. Yeah, so lambda x to y is continuous. Okay, so to prove this, we'll do this following claim. Credits to Bungo for pointing it out. So the claim is that proper subspaces have empty interiors. So the proof that he showed, like it goes something like this. So if we take proper subspace X of a topological vector space Y, and then we want to show the contradiction, so we take a point inside X and a point outside X. So let X be the inside point, Y be the outside point. So Y is in Y minus X. So then there exists a neighborhood u around 0, which will contain ty minus x for some t, and then x plus u will be inside x. So how do you see that there exists such a set? So since x is a, I mean, you take a neighborhood around x such that it falls inside, I mean, we assume that it has empty integers. So okay, wait, I didn't. Okay, so let's assume that x is not. I mean, x does not have empty interior. I forgot to write that here. So let's say x does not have empty interior. So then there will be a neighborhood u, which I mean a neighborhood v, which contains x and is inside x, since x is an, I mean, also let x be the interior point. So since v is inside x and contains x, so what we can do is we can translate v back to u, like the u which we saying here exists. We construct u by taking that neighborhood of x and scaling it back to u. So that's a neighborhood around 0. Now we need to find t such that ty minus x will be inside u. So now we do the opposite. So now what we do is we scale this down after a point so that u belongs here. I mean, it belongs to u. Okay. So so we change t so that after a point some. So yeah, so we scale, I mean, use some t so that ty minus x, or at least some lambda times t minus x for small lambda, will go inside u. So then from there we'll get that after translating back and doing some calculations, ty will be inside x, and so then y will be inside x because x is a subspace. I hope the logic makes sense here. I hope that's fine. This is fine, right? Hello?
That's fine.
Okay. Yeah. Thanks. Also, thanks to Bango for providing the proof. This actually was kind of tough to see. Okay. So now we'll come to the proof of the main theorem. So so now first note that since this is a convergent sequence, it is also a Cauchy sequence. So L will go inside C, right? That much is obvious. And since Y is an F space, Y is complete. So then the set where lambda n x is Cauchy is also the set where lambda n x is convergent. So then C is basically equal to L. So from 1 we get that L is equal to x, and since the limit exists, so lambda becomes continuous by looking at the image basically. So yeah, now okay, now we'll do this for 1. So from uniform boundedness principle, the sequence lambda n is bounded since lambda n x is Cauchy, and so a bounded sequence. So for all x in C, I think this is obvious that Cauchy implies boundedness for sequences. So then C becomes a subspace of X because if we take sum of two Cauchy sequences, that becomes Cauchy, and scaling a Cauchy sequence still gives a Cauchy sequence, because like if we want to see that after a point it goes inside a neighborhood or not. If we scale up the original Cauchy sequence, we can scale up the neighborhood as well, like, or scale it down the other way. So from there we can see that linear combination of Cauchy sequence becomes Cauchy. So therefore C becomes a subspace. Then by the claim that proper subspaces have empty interiors, so C is dense, because otherwise C, I mean, if C is not dense, then we can take C closure, then that is a proper subspace of X. So closed of a subspace, so that's a subspace, and it's a proper subspace since we're not taking it to be dense. So, and it will have empty interior. So by property 2, um, so we have we will arrive at a conclusion, and yeah, so C will fall under first category, which is a contradiction to our assumption. Yeah, this is fine, right? Until this point.
That looks good.
So far, so
Okay.
good.
Okay. So now we take X in X, and let's take W to be a neighborhood in Y around 0. So we want to see that X also will fall under C itself. That's what we want to see. So that for that we take a neighborhood, and then we'll try to see that if X will fall in W or not. So I mean the image of X under lambda n. So then by equicontinuity there exists a neighborhood V around 0 on X, such that lambda n V is in W for every n, since by the definition of equicontinuity. So since C is dense, we can find an X dash which is in C intersection X plus V. So we take this so that X dash minus X will fall under V. So the image of lambda n X minus X will fall under W for every n. And since C is dense, we can find such an X dash. So now, since lambda n X dash is Cauchy, so for a big enough n and m, so lambda n X dash and minus lambda m X dash goes inside W. Since W is a neighborhood in Y around 0, so then this will go closer and closer to 0. So then after one point, it will stay inside W. So now we do the usual trick in these cases. So for X, we'll see that lambda n X minus lambda m X, we just add and subtract a few points and breaking it into 3 parts basically. First one, which contains lambda n X minus X dash, which will be inside W, since X minus X dash is in V. Same goes for lambda m X dash minus X, which will also fall under W, and lambda n X dash minus lambda m X dash, which is our original Cauchy sequence. So that will also fall inside W. So this whole thing will fall under W plus W plus W, and that's also a neighborhood in Y around 0. So then from this we'll get that after a point there will exist n and m such that lambda n X minus lambda m X will fall inside a neighborhood around 0. So for a fixed neighborhood. So then from this we conclude that lambda n X is Cauchy, thus X is in C, which is what we need to complete the proof. Okay, so now we can modify this theorem as well using Baire category theorem and the categories. So like following. So if lambda n is a sequence of continuous linear mappings from an f space x into a topological vector space y, and if lambda x is just pointwise limit of lambda n's, I mean lambda defined to be pointwise limit of lambda n's, which exist for every x, then lambda is continuous. So first of all, since we have taken an f space, also I think this should be an f space y. Uh, in my Rudin, it says that it's a topological vector space, but I think it should be a f space because, like, as it says that here y needs to be an f space so that this lambda becomes continuous. But I don't know. So here, I mean, in my Rudin, it says that it doesn't need to be, but I think it should be f space. Okay, so basically
I think actually this proof doesn't use the previous theorem if I recall correctly. I initially thought that, but then I read it carefully, and he doesn't actually. He just makes a separate argument because he can't apply the previous theorem. So I think it is true even if y is not.
Yeah, I guess so. Like if we need to use the previous theorem, then probably this needs to be an f space, but I guess then he doesn't separate argument. I think I failed to see that. My bad. Okay, so the where we use the Baire category theorem here is in the fact that we take an f space. So basically, everything, like all of the subsets are of second category. So then, it should I mean it will exist for every x basically. So if it is a f space, it will follow from the previous theorem, and if not, I think Rudin will give an argument about that. I'm not going into that. So yeah, and now instead of like looking at completeness, we can look at compact convex sets. Then we get a different kind of result. So suppose x and y are topological vector spaces, k is a compact convex set in x, and gamma is a collection of continuous linear mappings of x into y, and the orbits for a point are bounded subsets of y for every point in k. So then there will be a bounded set B in y, subset of y, such that lambda of k is in B for every lambda in um, gamma. So what it does is that if we take a compact convex set and then look at the orbits being bounded, so if the orbits are bounded, then the whole image will be basically uniformly bounded. So for each map in the collection, the image of k under that map will be bounded by the same set. So basically same bound for all of them. So this is also kind of uniform boundedness principle, but in a different way. So yeah, now we'll look into open mapping and open mapping theorem, another application on Baire category theorem. So before the theorem, we need to understand what open mapping is. So suppose f is a map from S to T, where S and T are topological spaces. So we say that f is open at P if f of V contains a neighborhood of f of P, whenever V is a neighborhood of P. So basically, if P is open, and then if we take neighborhood of a point where it's open, then the image will also be open basically. So then we say that, it's kind of open because it's for one point. So now we say that f is open if and only if fu is open in T whenever u is open in T. So the open map just sends open sets to open sets. That's all it is. So now we look at the theorem. So suppose x is an f space, y is a topological vector space, gamma is a map, continuous linear map from x to y, and gamma of x is of the second category in y. Then gamma of x is equal to y, and gamma will be an open mapping, and y is an F space. So I didn't do the proof. I think you can read it up from Rudin, but since there is a mention of F space, so there will be use of the category, like there will be a category, I mean every subset of x will be a category, they will use it there. So I suggest you read it there. Sorry about that. And so we'll look at the corollaries from this. So there are many ways we can apply open up theorem, some of which are like this. So first of all, if A is a continuous linear mapping of an F space X onto an F space Y, then A is open. So this basically follows from this kind of directly itself. So since it's an open mapping, so if we map F space to an F space, then continuous linear mapping, then this itself will be open basically. So yeah, and if A satisfies 1 and is 1 on 1 by 1 to 1, then A inverse will be continuous. So basically what it says is, if it's a continuous bijection and is open, then it is a homeomorphism, which is quite a strong theorem, because like proving homeomorphisms in general is quite hard. But in this case, like if you have a continuous linear mapping from x to y, and both x and y are F space, and if it's 1 to 1, it is homeomorphism, which is great, because like then we can associate properties of x and y together. So now if x and y are Banach spaces, x and y are Banach spaces, and if A from x to y is continuous linear 1 to 1 and on to, so bijective, continuous linear and bijective, then there exists a positive real number A and B such that ax is norm of ax is bounded between A times norm of x and B times norm of x for every x in x. So this basically says that like it has a lower bound and an upper bound. So this part will come from, I think, being bounded above, and then this part will come from bound of A inverse, and then since we can like, show it in a cover it up in a ball, I think that's how we'll get that from the open mapping itself. So yeah, and so now if tau 1 tau 2 are two vector topologies where tau 1 is contained inside tau 2, so tau 2 is basically the bigger one, yeah, the bigger one or the coarser one, I think. Vector topologies on vector space X, and if both x tau 1 and x tau 2 are F spaces, then tau 1 equals to tau 2. So for this, we'll look into the identity map from X to X, which is a continuous linear map, and which is open as well. So then I think we send it from x tau 2 to x tau 1. Yeah, we take that to be identity. So then it's a continuous linear mapping, and then since these are F spaces, it will become open. So then tau 2 will go inside tau 1, because like the maps keeps the open sets intact. So any set which is open in tau 2 becomes open in tau 1. So then tau 1 will become tau 2. Yeah. So yeah. So now we'll look into the closed graph theorem. So now for Hausdorff spaces, there is a theorem like this. So if X is a topological space, Y is a Hausdorff space, and F is a map from X to Y, which is continuous, then the graph of f is closed. So by graph we mean the space, which we mean the set of the form x comma fx, where x is from x. So here, like, the image plays a very specific role. Like, we need it to be Hausdorff, because without Hausdorff this theorem does not hold. There is an example like this. Like, if we take real number, x to be r with lower limit topology, let's say, and then we take x cross x, y to be same as x, and f to be the identity map. So then the graph becomes the diagonal. Wait, no, I think it was opposite. Okay, no, never mind. Yeah, so no, if we take the map f which sends x to be, x to minus x, then the graph will be the off diagonal x comma minus x. I think that one is not closed. It's a different example, like, which says that you need y to be Hausdorff for this to hold. Okay. And the proof will probably be there in Mancres if you like feel like checking it out. It's there in exercises, which will basically walk you through the sketch of the proof, what you need to do. So yeah. Oh, the same argument works for the identity map. Oh, my bad. Yeah, I particularly remember the off diagonal one, but yeah, fine. If it works for identity, good. Yeah, graph being closed is basically equivalent to the Hausdorff condition. Yeah. So we do something similar for topological vector spaces. So let's assume that x and y are f spaces, A to be a linear map from x to y, and then G as a closed graph in x cross y. Then A becomes continuous. So this is quite powerful theorem in itself, because even checking continuity sometimes can be hard, but if you look at the graph and then say it's closed, that's kind of easier to show, proving that it's closed. So this makes our proving a map to be continuous becomes a bit easier. So again, I suggest you read the proof from Rudin. I haven't done this proof. So yeah, let's look at some applications. Okay, I think bilinear mapping theorem uses this as a fact. So yeah, we'll first of all we need to know what bilinear map is. So suppose x, y, z are vector spaces and B is a map from x cross y to z. So now we define a map. For every x and every y, we define the map bx and by. So here x is fixed and here y is fixed. So bx of y, this is small y, my bad, I just had a mistake. So bx of small y is bxy is by of x. So this is the map we're defining like this. So bxy is the bilinear map, which is defined as bx of y, and which is going to be the same as by of x. Like, these maps are defined by like that. So these maps bx by are defined like this. So b is bilinear if bx and by are linear. So basically, if we fix one coordinate, it becomes linear on the other. That's what bilinear means. Like, fix one variable and the other variables becomes linear. Multilinear goes in the same way. Like, there, instead of two, you will have multiple vector spaces, but that's out of our scope for now. So now we'll look at the theorem. So suppose B is a bilinear map from x cross y to z and separately continuous. Like, basically these maps bx and by are continuous. X is an f space and y, z are topological vector spaces. Then bx and yn will go to bx naught y naught in z whenever xn goes to x naught in x and yn goes to y naught in y. if y is metrizable, it follows that b is continuous. So how I think how the proof goes is so bxn yn, this you can look at as bxn of yn or byn of xn. So anyways, if you look at the, I mean, since bx and by are continuous graphs, so then I mean continuous maps, so their image we can look at, and then we can conclude that this happens in the graph basically. So then if y is metrizable, so if y becomes metrizable, then from there b becomes continuous. I suggest you look up the proof of this as well. And this is basically, I mean, it kind of looks the opposite way, because like there we had a map from x to y, we were looking at graph of it in x cross y. Here we are looking at a graph from x cross y to a different linear space basically, I mean topological vector space. So yeah, that's about it. Sorry if it felt a bit scuffed. Done. So yeah, any questions? You can hear me, right?
Yeah.
So any questions?
No, that was very good.
Okay, then I'll stop the recording.